Hey guys, how's it going? Okay, let's continue on the let's continue the book on page 12. Okay, here we go. This last change is an instance of a quite general rule in C. In any context where it is permissible to use the value of a variable of some type, you can use an expression of that type, since the third argument of printf has to be a floating point value to match the %6.1 lowercase f. Any floating point expression can occur there. The for itself is a loop, a generalization of the while. If you compare it to the earlier while, its operation should be clear. It contains three parts, separated by semicolons. The first part is done once before the loop proper is entered. The second part is the text. The second part is the test or condition that controls the loop. This condition is evaluated if it is true, the body of the loop. Here a single printf is executed. Then the reinitialization step is done, and the condition reevaluated. The loop terminates when the condition becomes false. As with the while, the body of the loop can be a single statement or a group of statements enclosed in braces. The initialization and reinitialization parts can be any single expression. The choice between while and for is arbitrary based on what seems clearer. The for is usually appropriate for loops in which the initialization and reinitialization are single statements and logically related, since it is more compact than while and keeps the loop control statements together in one place. Exercise 1-5. Modify the temperature conversion program to print the table in reverse order, that is from 300 degrees to 0. 1.4. Symbolic constants. A final observation before we leave temperature conversion forever. It's bad practice to bury magic numbers like 320 in a program. The convey little information to someone who might have to read the program later, and they are hard to change in a systematic, and they are hard to change in a systematic way. Fortunately, C provides a way to avoid such magic numbers. With the hash define construction at the beginning of a program, you can define a symbolic name or symbolic constant to be a particular string of characters. Thereafter, the compiler will replace all unquoted occurrences of the name by the corresponding string. The replacement for the name can actually be any text at all. It is not limited to numbers. The quantities lower, upper, and step are constants, so they do not appear in declarations. Symbolic names are commonly written in uppercase, so they can be readily distinguished from lowercase variable names. Notice that there is no semicolon at the end of a definition. Since the whole name after the defined name is substituted, there would be too many semicolons in the for. 1.5. A collection of useful programs. We're now going to consider a family of related programs for doing simple operations on character data. You will find that many programs are just expanded versions of the prototypes that we discuss here. Character input and output. The standard library provides programs for reading and writing a character at a time. GetChar fetches the next input character each time it is called and returns that character as its value. That is, after C equal getChar parentheses, the variable C contains the next character of input. Characters normally come from the terminal, but that need not concern us until Chapter 7. The function putChar is the complement of getChar. Prints the contents of variable C on some output medium. Again, usually the terminal. Calls to putChar and printf may be interleaved. The output will appear in the order in which the calls are made. As with printf, there is nothing special about getChar and putChar. They're not part of the C language, but they are universally available. File copying. Given getChar and putChar, you can write a surprising amount of useful code without knowing anything more about S-O. The simplest example is a program which copies its input to its output one character at a time in outline. Converting this into C gives the relation operator exclusive equal means not equal to. The main problem is detecting the end of the input. By convention, getChar returns a value which is not a valid character when it encounters the end of the input. In this way, programs can detect when they run out of input. The only complication is serious nuisance. A serious nuisance is that there are two conversions. A serious nuisance is that there are two conventions in common use about what the end of file value really is. We have deferred the issue by using the symbolic name EOF for the value, whatever it might be. In practice, EOF will be either -1 or 0, so the program must be preceded by the appropriate one of. In order to work properly, by using the symbolic constant EOF to represent the value that getChar returns when end of file occurs, we are assured that only one thing in the program depends on the specific numeric value. We also declare C to be an int, not a char, so it can hold the value which getChar returns. As we shall see in chapter 2, this value is actually an int, since it must be capable of representing EOF in addition to all possible chars. The program for copying would actually be written more concisely by experienced C programmers. In C, any assignment such as C equal getChar parentheses can be used in an expression. Its value is simply the value being assigned to the left-hand side if the assignment of a character to C is put inside the test part of a while the file copy program can be written. The program gets a character, assigns it to C, and then tests whether the character was the end of file signal. If it was not, the body of the while is executed, printing the character. The while then repeats it. The while then repeats. When the end of the input is finally reached, the while terminates, and so does main. This version centralizes the input. There is now only one call to getChar and shrinks the program. Nesting an assignment in a test is one of the places where C permits a valuable conciseness. It's possible to get carried away and create impenetrable It's possible to get carried away and create impenetrable code, though a tendency that we will try to curb. It's important to recognize that the parentheses around the assignment within the conditional are really necessary. The precedence of exclusive equal is higher than that of equal, which means that in the absence of parentheses, the relational test exclusive equal would be done before the assignment equal. So the statement is equivalent to like this. This has the undesired effect of setting C to 0 or 1 depending on whether or not the call of getChar encountered in the file. More on this in chapter 2. Character counting. The next program counts characters. It is a more elaboration of the copy program. The statement ++nc semicolon shows a new operator plus or double pluses or a pair of pluses, which means increment by 1. You could write nc equal nc plus 1, but ++nc is more concise and often more efficient. There is a corresponding operator minus to decrement by 1 the operators plus and minus or subtracts can be either prefix operators ++nc or postfix nc++. These two forms have different values in expressions, as will be shown in chapter 2. But ++nc and nc++ both increment nc. For the moment, we will stick to prefix. For the moment, we will stick to prefix. The character counting program accumulates its count in a long variable instead of an int. On a PDP-11, the maximum value of an int is 32767, and it would take relatively little input to overflow the counter if it were declared int. In Honeywell and IBM C, long and int are synonyms. Long and int are synonyms and much larger. The conversion specification %LD signals to printf that the corresponding argument is a long integer. To cope with even bigger numbers, you can use a double length float. We will also use a for statement instead of a while to illustrate an alternative way to write the loop. Printf uses lowercase f for both float and double. %.0 lowercase f suppresses printing of the non-existent fraction part. The body of the for loop here is empty because all of the work is done in the test and reinitialization parts, but the grammatical rules of C require that a for statement have a body. The isolated semicolon, technically a null statement, is there to satisfy that requirement. We put it on a separate line to make it more feasible. Before we leave the character counting program, observe that if the input contains no characters, the while or for test fails on the very first call to get char, and so the program produces 0. The right answer. This is an important observation. One of the nice things about while and for is that they test at the top of the loop before proceeding with the body. If there is nothing to do, nothing is done, even if that means never going through the loop body. Programs should act intelligently. One-handed input like no characters. The while and for statements have ensured that they do reasonable things with boundary conditions. 9. Counting. The next program counts lines in its input. Input lines are assumed to be terminated by the new line character \m that has been religiously appended to every line written out. The body of the while now consists of an if, which in turn controls the increment and L. The if statement tests the parenthesized condition, and if it is true, does this statement or group of statements embraces that follows. We have again indented to show what is controlled by what. The double equals sign. The double equals sign, equal, or a pair of equals, double equals, is the C notation for is equal to, like for instance, EQ. This symbol is used to distinguish the equality test from the single equal for assignment. Used this symbol is used to distinguish the equality test from the single equal used for assignment. Since the assignment is about twice as frequent as equality testing in typical C programs, it's appropriate that the operator be half as long. Any single character can be written between single quotes to produce a value equal to the numerical value of the character in the machine's character set. This is called a character constant. So, for example, single quote uppercase A is a character constant in the ASCII character set. Its value is 65. The internal representation of the character uppercase A, of course, single quote uppercase A is to be preferred over 65. Its meaning is obvious, and it is independent of a particular character set. The escape sequences used in character strings are also legal in character constants. So in tests and arithmetic expressions, single quote /n stands for the value of the new line character. You should note carefully that single quote /n is a single character, and in expressions is equivalent to a single integer. On the other hand, double quote \n is a character string which happens to contain only one character. The topic of strings versus characters is discussed further in Chapter 2. Exercise 1-6. Write a program to count blanks, tabs, and new lines. Exercise 1-7. Write a program to copy its input to its output, replacing each string of one or more blanks by a single blank. Exercise 1-8. Write a program to replace each tab by the 3-character sequence greater than backspace minus, which prints as arrow, and each backspace by the similar sequence back arrow. This makes tabs and backspaces feasible. Word counting. The fourth in our series of useful programs counts lines, words, and characters with the loose definition that a word is any sequence of characters that does not contain a blank, tab, or new line. This is a bare-bones version of Unix utility WC. Every time the program encounters the first character of a word, it counts it. The variable in word records whether the program is currently in a word or not. Initially, it is not in a word, which is assigned the value no. We prefer the symbolic constants yes and no to the literal values 1 and 0 because they make the program more readable. Of course, in a program as tiny as this, it makes little difference. But in larger programs, the increase in clarity is well worth the modest extra effort to write it this way originally. You will also find that it's easier to make extensive changes in programs where numbers appear only as symbolic constants. The line NL equal NW equal NC equal 0 semicolon sets all three variables to 0. This is not a special case, but a consequence of the fact that an assignment has a value and assignments associate right to left. It's really as if we had written. The operator bar means or, so the line says if C is a blank or C is a new line or C is a tab. The escape sequence \t is a visible representation of the tab character. There is a corresponding operator ampersand for and. Expressions connected by ampersand or bar are evaluated left to right, and it is guaranteed that evaluation will stop as soon as the truth or falsehood is known. Thus, if C contains a blank, there is no need to test whether it contains a new line or tab, so these tests are not made. This isn't particularly important here, but is very significant in more complicated situations, as we will soon see. The example also shows the CL statement, which specifies an alternative action to be done if the condition part of an if statement is false. The general form is one and only one of the two statements associated with an if-else is done. If the expression is true, statement 1 is executed. If not, statement 2 is executed. Each statement can in fact be quite complicated. In the word count program, the one after the else is an if that controls two statements. In braces, exercise 1 middle score 9. How would you test the word count program? What are some boundaries? Exercise 1 middle score 10. Write a program which prints the words in its input, 1 per line. Exercise 1 middle score 11. Revise the word count program to use a better definition of word. Double quote is word. For example, a sequence of letters, digits, and apostrophes that begins with a letter. 1.6. Erase. Let us write a program to count the number of occurrences of each digit of white space characters, blank, tab, new line, and all other characters. This is artificial. Of course, it permits us to illustrate several aspects of C in one program. There are 12 categories of input, so it is convenient to use an array to hold the number of occurrences of each digit rather than 10 individual variables. Here is one version of the program. The declaration declares n digit to be an array of 10 integers. Array subscripts always start at 0 in C rather than 1 as in Fortran or PS-I. So the elements are like this. This is reflected in the for loops which initialize and print the array. A subscript can be any integer expression, which of course includes integer variables like I and integer constants. This particular program relies heavily on the properties of the character representation of the digits. For example, the test determining whether the character in C is a digit. If it is, the numeric value of that digit is. This works only if single quote 0, comma, single quote 1, etc. are positive and in increasing order. And if there is nothing but digits between single quote 0 and single quote line, fortunately, this is true for all conventional character sets. By definition, arithmetic involving character. By definition, arithmetic involving chars and ints converts everything to int before proceeding, so char variables and constants are essentially identical to ints in arithmetic context. In arithmetic context, this is quite natural and convenient. For example, this is quite natural and convenient. This is quite natural and convenient. For example, C minus single quote 0 is an integer expression with a value between 0 and line corresponding to the character single quote 0 to single quote line stored in C, and is thus a valid subscript for the array n digit. The decision as to whether a character is a digit, a white space, or something else is made with the sequence. The pattern occurs frequently in programs as a way to express a multi-way decision. The code is simply read from the top until some condition is satisfied. At that point, the corresponding statement part is executed, and the entire construction is finished. Of course, statement can be several statements enclosed in braces. If none of the conditions is satisfied, the statement after the final else is executed if it is present. If the final else and statement are emptied, as in the word count program, no action takes place. There can be an arbitrary number of groups between the initial if and the final else. As a matter of style, it is advisable to format this construction as we have shown, so that long decisions do not march off the right side of the page. The switch statement to be discussed in Chapter 3 provides another way to write a multi-way branch that is particularly suitable when the condition being tested is simply whether some integer or character expression matches one of a set of constants. For contrast, we will present a switch version of this program in Chapter 3. Exercise 1 score 12. Write a program to print a histogram of the length of words in its input. It is easiest to draw the histogram horizontally A vertical orientation is more challenging. 1.7 Functions. In C, a function is equivalent to a subroutine or function in Fortran, or a procedure in PL/I, Pascal, etc. A function provides a convenient way to encapsulate some computation in a black box, which can then be used without worrying about its innards. Functions are really the only way to cope with the potential complexity of large programs. With properly designed functions, it is possible to ignore how the job is done. Knowing what is done is sufficient. C is designed to make the use of functions easy, convenient, and efficient. You will often see a function only a few lines long called only once, just because it clarifies some piece of code. So far, we have used only functions like printf, getchar, and putchar that have been provided for us. Now, it is time to write a few of our own. Since C has no exponentiation operator like the asterisk or star of Fortran or PL/I, let us illustrate the mechanics of function definition by writing a function power parenthesis m comma n to write an integer m to a positive integer power n. That is, the value of power parenthesis 2 comma 5 is 32. This function certainly doesn't do the whole job of a star since it handles only positive powers of small integers, but it is best to confuse only one issue at a time. Here is the function power and a main program to exercise it. You can see the whole structure at once. Like this. The functions can appear in either order, and in one source file or in two. Of course, if the source appears in two files, you have to say more to compile and load it than if it all appears in one. But that is an operating system matter, not a language attribute. For the moment, we will assume that both functions are in the same file, so whatever you have learned about running C programs will not change. The function power is called twice in the line. Each all passes 2 arguments to power, which each time returns an integer to be formatted and printed. In an expression, power parenthesis 2 comma I is an integer just as 2 and I are. Not all functions produce an integer value. We will take this up in chapter 4. In power, the arguments have to be declared appropriately so their types are known. This is done by the line. That follows the function name. The argument declarations go between the argument list and the opening left brace. Each declaration is terminated by a semicolon. The names used by power for its arguments are purely local to power and not accessible to any other function. Other routines can use these same names without conflict. This is also true of the variables I and p. The I in power is unrelated to the I in main. The value that power computes is returned to main by the return statement, which is just as in P/I. Any expression may occur within the parentheses. A function need not return a value. A return statement with no expression causes control but no useful value to be returned to the caller. It starts falling off the end of a function by reaching the terminating right brace. Exercise 1. Middle score 13. Write a program to convert its input to lowercase using a function lower parenthesis c, which returns c if c is not a letter, and the lowercase value of c if it is a letter. Arguments 1.8 Arguments. Call by value. One aspect of C functions may be unfamiliar. To programmers who are used to other languages, particularly Fortran and P/I in C. All function arguments are passed by value. This means that the called function is given the values of its arguments in temporary variables actually on a stack, rather than their addresses. This leads to some different properties than are seen with call by reference languages like Fortran and P/I, in which the called routine is handed the address of the argument, not its value. The main distinction is that in C, the called function cannot alter a variable in the calling function. It can only alter its private temporary copy. Call by value is an asset. However, not a liability. It usually leads to more compact programs with fewer extraneous It usually leads to more compact programs with fewer extraneous variables. Because arguments can be treated as conveniently initialized local variables in the called routine. For example, here is a version of Power which makes use of this fact. The argument n is used as a temporary variable. The argument n is used as a temporary variable and is counted down until it becomes 0. There is no longer a need for the variable I. Whatever is done to n inside Power has no effect on the argument that Power was originally called with. When necessary, it is possible to arrange for a function to modify a variable in a calling routine. The caller must provide the address of the variable to be set, technically a pointer to the variable, and the called function must declare the argument to be a pointer and reference the actual variable indirectly through it. We will cover this in detail in Chapter 5. When the name of an array is used as an argument, the value passed to the function is actually the location or address of the beginning of the array. There is no copying of array elements. By subscripting this value, the function can access and alter any element of the array. This is the topic of the next section. 1.9 Character Arrays. Probably the most common type of array is the array of characters. To illustrate the use of character arrays, the functions to manipulate them, let's write a program which reads a set of lines and prints the longest. The basic outline is simple enough. This outline makes it clear that the program divides naturally into pieces. One piece gets a new line, another tests it, another saves it, and the rest controls the process. Since things divide so nicely, it would be well to write them that way too. Accordingly, let us first write a separate function getLine to fetch the next line of input. This is a generalization of getChar to make the function useful in other contexts. We will try to make it as flexible as possible. At the minimum, getLine has to return a signal about possible end of file. A more generally useful design would be to return the length of the line, or 0 if end of file is encountered. 0 is never a valid line length, since every line has at least one character. Even a line containing only a new line has length 1. When we find a line that is longer than the previous longest, it must be saved somewhere. This suggests a second function, copy the copy to the new line to a safe place. Finally, we need a main program to control getLine and copy. Here is the result. Main and getLine communicate both through a pair of arguments and a returned value. In getLine, the arguments are declared by the lines, which specify that the first argument is an array and the second is an integer. The length of the array S is not specified in getLine since it is determining the main. getLine uses return to send a value back to the caller, just as the function power did. Some functions return a useful value, others like copy are only used for their effect and return no value. getLine inputs the character \0, the new character whose value is 0, at the end of the array it is creating, to mark the end of the string of characters. This convention is also used by the C compiler when a string constant like is written in a C program. The compiler creates an array of characters containing the characters of the string and terminates it with a \0 so that functions such as printf can detect the end. The %s format specification in printf expects a string represented in this form. If you examine copy, you will discover that it too relies on the fact that its input argument S1 is terminated by \0, and it copies this character onto the output argument S2. All of this implies that \0 is not a part of normal text. It is worth mentioning in passing that even a program as small as this one presents some sticky design problems. For example, what should main do if it encounters a line which is bigger than its name? GetLine works properly in that it stops collecting when the array is full, even if no new line has been seen. By testing the length and the last character returned, main can determine whether the line was too long and then cope as it wishes. In the interest of brevity, we have ignored the issue. There's no way for a user of GetLine to know in advance how long an input line might be. So GetLine checks for overflow. On the other hand, the user of copy already knows or can find out how big the strings are. So we have chosen not to add error checking to it. Exercise 1 minute score 14. Revise the main routine of the longest line program so it will correctly print the length of arbitrarily long input lines and as much as possible of the text. Exercise 1 minute score 15. Write a program to print all lines that are longer than 80 characters. Exercise 1 minute score 16. Write a program to remove trailing blanks and tabs from each line of input and to delete entirely blank lines. Exercise 1 minute score 17. Write a function reverse parenthesis s which reverses the character string s. Use it to write a program which reverses it input a line at a time. 1.10 Scope External Variables. The variables in main line parenthesis line comma save etc. are private or local to main because they are declared within main. No other function can have direct access to them. The same is true of the variables in other functions. For example, the variable I in getLine is unrelated to the I in copy. Each local variable in a routine comes into existence only when the function is called and disappears when the function is excited. It is for this reason that such variables are usually known as automatic variables. Following terminology in other languages. We will use the term automatic henceforth to refer to these dynamic local variables. Chapter 4 discusses the static storage class, in which local variables do retain their values between function invocations. Because automatic variables come and go with function invocation, they do not retain their values from one call to the next, and must be explicitly set upon each entry. If they are not set, they will contain garbage. As an alternative to automatic variables, it is possible to define variables which are external to all functions, that is, global variables which can be accessed by name by any function that cares to. This mechanism is rather like Fortran common or PS-external. Because external variables are globally accessible, they can be used instead of argument lists to communicate data between functions. Furthermore, because external variables remain in existence permanently, rather than appearing and disappearing as functions are called and excited. They retain their values even after the functions that set them are done. An external variable has to be defined outside of any function. This allocates actual storage for it. The variable must also be declared in each function that wants to access it. This may be done either by an explicit external declaration or implicitly by context. To make the discussion concrete, let us rewrite the longest line program with line, save, and max as external variables. This requires changing the calls, declarations, and bodies of all three functions, like this. The external variables in main, getLine, and copy are defined by the first lines of the example above, which state their type and cause storage to be allocated for them. Syntactically, external definitions are just like the declarations we have used previously, but since they occur outside of functions, the variables are external. Before a function can use an external variable, the name of the variable must be made known to the function. One way to do this is to write an external declaration in the function. The declaration is the same as before except for the added keyword external. In certain circumstances, the external declaration can be emptied. If the external definition of a variable occurs in the source file before it's used in a particular function, then there is no need for an external declaration in the function. The external declarations in main, getLine, and copy are thus redundant. In fact, common practice is to place definitions of all external variables at the beginning of the source file, and then omit all external declarations. If the program is on several source files and a variable is defined in, say, file 1 and used in file 2, then an external declaration is needed in file 2 to connect the two occurrences of the variable. This topic is discussed at length in chapter 4. You should note that we are using the words declaration and definition carefully. When we refer to external variables in this section, definition refers to the place where the variable is actually created or is assigned storage. Declaration refers to places where the nature of the variable is stated but no storage is allocated. By the way, there is a tendency to make everything inside an external variable because it appears to simplify communications. Argument lists are short and variables are always there when you want them. But external variables are always there even when you don't want them. This style of coding is fraught with peril since it leads to programs whose data connections are not at all obvious. Variables can be changed in unexpected and even inadvertent ways, and the program is hard to modify if it becomes necessary. The second version of the longest line program is inferior to the first, partly for these reasons and partly because it destroys the generality of two quite useful functions by writing into them the names of the variables that will manipulate. Exercise 1, middle score 18. The test in the fourth statement of get line above is rather ungainly. Rewrite the program to make it clearer, but retain the same behavior at the end of file or buffer overflow. Is this behavior the most reasonable? 1.11 Summary. At this point we have covered what might be called the conventional core of C. With this handful of building blocks, it is possible to write useful programs of considerable size, and it would probably be a good idea if you paused long enough to do so. The exercises that follow are intended to give you suggestions for programs of somewhat greater complexity than the ones presented in this chapter. After you have this much of C under control, it will be well worth your effort to read on for the features covered in the next few chapters are where the power and the expressiveness of the language begin to become apparent. Exercise 1, middle score 19. Write a program dtab which replaces tabs in the input with the proper number of blanks to space to the next tab stop. Assume a fixed set of tab stops, say every n positions. Exercise 1, middle score 20. Write a program in tab which replaces strings of blanks by the minimum number of tabs and blanks to achieve the same spacing. Use the same tab stops as for dtab. Exercise 1, middle score 21. Write a program to fold long input lines after the last non-blank character that occurs before the nth column of input, where n is a parameter. Make sure your program does something intelligent with very long lines, and if there are no blanks or tabs before the specified column. Exercise 1, middle score 22. Write a program to remove all comments from a C program. Don't forget to handle quoted strings and character constants properly. Exercise 1, middle score 23. Write a program to check a C program for rudimentary syntax errors like unbalanced parentheses, braces, and braces. Don't forget about quotes, both single and double, and comments. This program is hard if you do it in full generality. Okay, it's time to take a break. I'm gonna pee. Goodbye.